Okay, the objective of these notes is to develop a PD control for the inverted pendulum. Remember the position of the card is Z and the angle is theta. And in a previous notes, we derived the open loop transfer function to be m1g over m2 divided by s plus b over m2, and that was the transfer function from theta to z, and then the transfer function from f to theta was given by minus 1 over m2l divided by s squared minus m1 plus m2g divided by m2l. And because we don't want to keep writing all these coefficients, let's just define some simple things like a1 to be 1 over m2l, a2 to be m1 plus m2g over m2l, and a3 to be m1g over m2. And that results in the revised system that looks like this with these coefficients, so it'll be a little bit easier. Now we also note that the force for any real system, the force is going to be saturated. So this would be F max minus F max, which means that the signal that comes in on the right hand side is saturated. It can't get above F max or below minus F max, and so if the signal is in between those values, then it just passes through the saturation block, but otherwise it's clipped at plus or minus F max. And the force, the maximum force, actually determines in many ways the possible performance of the system. Okay, so the idea we're going to use to develop the control system for this particular system is something called successive loop closure. And the idea is that we're going to wrap a PD controller around the inner loop. So on the inner loop here, we're going to wrap a PD controller. So we'll have KP theta and KD theta S plus minus, and this is going to be theta desired, and then we make a loop, we wrap feedback around theta. The idea is to design the inner loop, so this would be the inner loop. We'll do a PD control for the inner loop, and then if the inner loop is much faster than the outer loop, we can replace the inner loop by its DC gain and then do a subsequent design on the outer loop. And the design on the outer loop will be, again, to wrap PD control. So if this is our desired cart position, we'll wrap feedback in this way. So this would be KPZ, and then KDZS. Like this, and so this is the outer loop. And successive loop closure basically takes these loops one at a time. So we're going to go through how to do this inner loop, outer loop design. Okay, so the idea is to first work on the inner loop, and let me redraw just the inner loop. So this is theta desired. Our objective now is to systematically choose the gains Kp theta and Kd theta to maximize the performance of the system given the constraints. So along those lines, I just want to point out that if you have a step function of size A, okay, and then you design a system so it has a certain rise time. In other words, you pick the poles of the system, to be at some location given by omega n e to the j plus or minus theta, where theta is theta equals the sine inverse of the damping coefficient zeta. So there's a particular rise time, and the rise time is roughly 2.2 divided by omega n. So it's inversely proportional to the magnitude of the complex poles. If you apply, my point here is that if you apply a step of size 2a, what will be the rise time? And the answer is that it's exactly the same. So the 10%, 9% is exactly the same rise time. So the pole location gives rise time for any step. However, the magnitude of the force that will be required to achieve that step will, of course, increase. So if the force is limited, then that limits the rise time that you can achieve for a given step. So to say get the fastest possible response you can get for a given step, subject to the constraints of F max, the objective, we need to choose Kp correctly. So the way to reason about the system is to consider the case where theta of t is stationary for a period of time, and then you get a step of size a theta on theta desired. So if this is the time history, theta and theta desired. So if theta desired comes along and makes a step of a theta, and if theta has been constant over this time period, then notice that theta at this point, or has been 0, is 0, and the derivative is also 0. So right after the step, it takes a moment for the derivative to kick in. Instantaneously after the step is applied, the only signal comes through this path. And so, we can say, assuming, we can say that the force, F, is going to be equal to Kp theta times A theta. And the idea is that we're going to, for a step size of theta, if this is, say, the maximum step size we might see, then we're going to make this equality hold where F is equal to F max. So that gives us a formula for Kp theta that in some sense maximizes the performance of the system. So it's F max over A theta. And again, the idea is that the choice of Kp theta is to achieve maximum force precisely at the moment after a step of size 8 theta is applied. Okay, so we've picked AP theta, and now the idea is to find a method for choosing the derivative gain, Kd. And the idea there is that we derive the transfer function, so the actual closed loop, the actual closed loop transfer function, and we can derive it as follows. Theta of s, so after a little bit of manipulation, we get theta of s equals minus a1 kp theta divided by s squared minus a1 kd theta minus a2 plus a1 kp theta times theta desired of s. So this is the actual transfer function, and then the idea is to set this equal to the desired closed loop transfer function. And I'm going to just append this with a theta, denoting, noting that this is for the inner loop subsystem. So equating the denominators of these two equations, we get the following expression. We can solve for omega n as the square root of minus a2 plus a1 kp theta. Oh, and that reminds me, coming back up here, for the inverted pendulum, notice that to get a positive theta, okay, we would need to move the cart. We would have to exert a negative force. And so the gain here will be a negative kp, because negative force will produce positive angles. Okay, so kp theta will be negative in this particular case, and in part that's dictated by the negative gain here in the open loop transfer function. Okay, so back at this point, that implies that this term will be negative, and if it dominates A2, that omega n, and of course that's a constraint, omega n needs to be positive. Okay, so setting the second equations, or the second terms in these expressions here equal, we can solve for k d theta equal to minus 2 zeta omega n divided by a1. And there's our expression for the derivative gain. Now, one last thing I want to note is that we need to find the DC gain of this system. So if we come back here, if we come back to the actual transfer function, you'll note that the DC gain, so let's call it KDC, is equal to the limit as s goes to 0 of h of s, where this transfer function is defined as h of s, and that means that the DC gain is equal to a1 kp theta divided by a2 plus a1 kp theta. Okay, and that this term, you'll notice, will be less than 1. And what that means simply is that if we apply a step of theta desired, at this point, that theta will actually rise up, and the steady state value here will be k dc theta desired. Okay, so we have designed the inner loop, meaning we've found an expression for kp theta and for kd theta, and there are two parameters that we can tune. So to tune the inner loop, we can change a theta and also the damping ratio zeta of theta. Okay, so now we want to come back here to our main system, and the idea is to do the outer loop. And so what we will assume is that the inner loop is faster, or converges at a faster time scale than the outer loop. And so this entire inner loop here, this whole thing can be replaced by the DC gain of the system. So we're going to replace it by KDC. So let's redraw then the outer loop. So I'm going to come back here. Let's see. Okay, so I have redrawn the outer loop system where I've replaced the inner loop with its DC gain. Okay, and this allows me now to be back to designing a second order system where PD control is a technique that makes sense. Okay, so again, we're going to go through the same analysis. We assume that we're going to place a step on the system of AZ, and we assume that the system is initially at rest. So if the system's at rest, it's 0 and its derivative of 0 before the step. So right after the step then, the signal that is applied at this point, which is theta desired, is going to be theta desired equal to kpz times az, because z is originally at 0 and its derivative is originally at 0. So if we set this equal to the maximum step size that we've decided to put on theta d to get our performance, to get the maximum possible performance. In other words, when there's a step of az, we're going to apply the maximum possible force right at that point. And at that point, theta d is equal to a theta, and so that implies that our kpz is a theta over a z. And again, both a theta and az are gains that we will tune in the system. Okay, so there's our expression for the proportional gain on the outer loop, and now we just need to find the derivative gain by setting the actual transfer function equal to the inner transfer function. So the actual transfer function can be derived as, the transfer function after a little bit of manipulation can be derived by this expression. And the idea is that we want to now set that equal to desired transfer function, which we can set equal to omega n z squared over s squared plus 2 zeta z omega n z s plus omega n z squared times z desired of s. And setting the denominators of these two expressions equal to each other, we get that omega n z is the square root of a3 k dc kpz, where we've already chosen kpz, and then k dz is going to be equal to 2 zeta z omega n z minus b over m3 all divided by k dc a3. So there's our expression for the derivative gain. So we have accomplished our design for the outer loop and for the inner loop. So for the outer loop, here's the proportional gain. There is the derivative gain. This is, that's k dz. And what do we tune for the overall system? We tune the maximum step size, a theta, which, maximum force is applied, and the maximum step size, az, for which the maximum step is applied. Also, the damping coefficient of the inner loop and the damping coefficient of the outer loop. And typically an initial place to start with these is 0.707. Okay, so that's the design for the inverted pendulum, and you can download the implementation in Simulink on the